just for confirmation, you should see live, correct?
Correct.
Okay, thank you.
Yeah, I got it.
Good morning, everybody. For those who have joined early to our meeting, we have a Teams live event that we will do for you today. And during this event, you won't be able to speak, but we can field your questions and you can type your questions. So if you want to take a moment to look on your screen, in the upper right corner is a little question mark icon. And if you click that icon, it will open like the questions window. And you'll have the ability to ask questions that way. And as when that window opens, we would ask down on the bottom, there's a section that you can enter your name or change your name. It says either you or anonymous. And if you would just type your name in that little box, this way, if you do make a comment or ask a question, we know who it is. We would ask you to do that for us, please. So the meeting is not started yet. Please be patient and we'll start in a moment. Good morning, everybody. Just wanted to let you know we are here. We'll wait another minute or two for the guys that are lingering to join, so please be patient. If you have a moment and you just joined, we ask that if you would like to ask some questions during this live event, you'll only be able to do so by text. And so in the upper section of your screen, there's a little question mark icon you can click on, and then you can open the questions window. And then we ask you, in the bottom of the questions window is a section that says your name. It's either you or anonymous. And we ask that you enter your name. And if any questions are asked, we know who asked that question. So we'll be back in just a minute. Thank you for joining. Okay, everyone, good morning, and thank you for joining us today. Our live event offered by Marubeni Citizen-Cincom today will be on the LFV technology. And before we start, I'd like to give a little introduction. As we want to prepare our presentation, there's you can approach this on a very technical basis, or you can approach it simply on a sales basis. And basically our LFV technology is just very easy to use, and it just works. And we're going to show you different videos, but we thought you have to understand some of the concepts. So there's a little bit of the engineering involved in this. We're trying to keep it, we might be 30 to 45 minutes. We'll see how we do and with your questions. And as many of some of our competitors are coming out with or have come out with similar, what they say is similar technologies, we want to tell you that we want to report to you our LFV technology is the starting of all of it. And we want to explain our technology to you. So today we have our engineer from MCC, Illinois, Mr. Brad Warren, and he'll be giving the event today. So Brad, please introduce yourself and please continue.
Good morning, everyone. I'm Brad, and I'd like to go ahead and begin with our presentation today. So today we're going to be talking about LFV, and some of the points we're going to get to is what is it, what materials benefit from it, how it works, machines offered, the ease of programming, proper speeds and feeds, and some insert concepts. So let's dive right into it. What is LFV? It is a very controlled sink from spindle to axis to produce a vibrating cutting method with a series of air cuts to break the chip. As you can see in the figure below, this is how the LFV looks if you were to unwrap the cut. We have our first cut during a revolution with an air cut going in at the second pass. So on this first video I want to show you is it's an older graphic, but we feel it best describes the process of LFV. Even though this is not a Swiss concept, it is the same though. So in the first image, this shows oscillation perfectly timed with the spindle rotation, moving in and out of the cut, creating a corrugated surface, or as you may know as the bump. So the cut moves in and away. So if we were to go ahead and we were to if we were to dissect this a little bit more and unwrap the process, you can see the tool is corrugated surface moves out and comes back in perfectly timed to hit that corrugated surface again. So again, here's a deeper look at the view unwrapped within a 360-degree one revolution.
So I'd like to add for a second. So if we look at some of the possible things out there that are trying to simulate this technology, the others will move forward in a cut and back up a little bit, move forward in a cut and back up a little bit. And when they come in to cut again, they're actually hitting a straight wall. There's no technology behind their process. And they're taking the tool and hitting the turned surface, the turned wall. So the technology of the LFV technology in that slide is very deeply showing that we are leaving a very perfectly timed corrugated pattern on the face of the shoulder. So as the tool comes in again, it's hitting perfectly this corrugation, not a direct wall. And as Brad continues, there's many slides that are going to show some of this, and he's got to make sure that you understand that first is the key. And now the next slides will keep continuing to demonstrate this process. So go ahead, Brad.
Thank you, Brian. So what materials would this benefit in all this? LFV, it can benefit many materials, but more specifically, we can benefit from Inconel, our stainless steels, our coppers, our pure irons, plastics, and any other difficult to cut materials. As you can see on the picture on the right, we have some differences with our LFV cutting versus our conventional cutting. Those are the same amount of chips, but greatly reduced into smaller chip patterns with the LFV cutting. Now just a little quick video of some nylon running. In this video, we'll move it up a little bit. So as you can see with the turning of the nylon here, it's breaking the chips very evenly on the turn, and it's just works beautifully. Another video of nickel silver with LFV. And here, it's a tough material. As you can see, does get chip breaking issues. Chips getting wrapped around the part, creating a little bird's nest. On the right hand side though, with the LFV, no chips being balled up. So it works wonderfully.
Also, the reminder that it works in the x-axis also for the grooving and cutoff.
So on a video like this, and a part like this, you probably would have damaged your collet and maybe some other things at that point in time. So LFV really does benefit Getting into more benefits of LFV. It's ideal for difficult to machine materials, reductions in downtime, increase in productivity, efficient through combinations of vibrations and standard cuttings, difficult to machine pieces, great for deep hole drilling, easy to program, programmable chip control. This was a test I did a little while back in 17.4. On the left-hand side is LFV off, and you can just see the chips are just massive. But with the LFV on, chips are very controlled, small, and cut beautifully. Some continued benefits: chips are broken up and don't become entangled in materials or tools. Cutting resistance is lowered. Reduction or the removal of high pressure coolant. High pressure coolant can be our best friend, but sometimes it can be our own worst enemy. No built up edges. Machining temperature doesn't rise, so less thermal distortion, and you have extended tool life. Getting into how it works. There are three modes. Mode 1, the multiple oscillations per revolution. Mode 2, the multiple revolutions per oscillation. And mode 3, threading, the x-axis oscillates for each threading pass. What applications can each mode offer? Mode 1, again, is multiple oscillations per revolution, which is great for cutting difficult materials, turning, grooving, drilling, and cutoff. Mode 2 multiple revolutions per oscillation, which is great for smaller materials, small drill, where a higher surface footage may be needed. And then mode 3 is your x-axis oscillates while you're threading.
So let me interrupt for a second. We did have a question, and I could either let them all build up or we might throw them in there in the middle. I thought I would ask this one. So it doesn't pertain exactly to where you are. It's like a statement. Someone said, Star is telling customers their LFV type option is backwards compatible to older models. So we have some sales staff supporting in this meeting also. Would anybody like to make a comment to that, guys?
Well, our machines are, as I say, we don't just have the software function. The machine is actually built to withstand these oscillations and cutting forces. So the machine is actually different. It's not just a software function, which I believe that's why Star's saying that. They can just install possibly a different macro for turning, whereas our machine is actually built around and for LFV.
Thank you, Tim. And I'm going to add to that. As I said in the beginning introduction, our competitors, and one of them, Star, basically is moving forward and backing up and moving forward and backing up. There's no technology there. So their turning insert will be hitting, for the lack of a better word, the turned wall straight on, which produces a lot of cutting pressure and is not good for a turning tool. The LFV is not just a motion of back and forth, it's this perfectly timed producing a corrugated surface, which totally changes the cutting pattern. And so we can't just put it on an old machine, as was just described. Our machines are made to withstand this vibration, And of course, if you didn't have this technology, you could do that on a 30-year-old machine. So the ability to move forward and back. So, and that's our goal, to have these events, is to explain our technology and you can see for yourself in the end. So thank you for the question or the statement, and I'll ask Brad, please continue.
Thank you, Brian. So what machines, so moving forward, what machines do we currently, or what machines do we offer LFV? These are the machines that we offer LFV on, with a few exceptions I wanted to cover really quick. Your A320, it is available on via special order, but also keep in mind it's only available in mode 1. Modes 2 and 3 are not available. And on the L220, type 8 and type 9, the X2 and Z2 are available, but on the type 10 and type 12, it is not available due to the Y-axis. On the L32, the X2 and Z2 on all types is available, but it is reduced to a lower vibration. So just keep that in mind. I want to go ahead and I want to move forward to programming and utilization of LFV. LFV, again, is just easy to use. It's easy to add to any NC program. Rapid moves are not allowed during modes 1 and 2, but G0C is allowable. G code's not usable. I'm not going to go through all these. Most of these are, if you kind of look at them, it's just kind of common sense on why they won't go ahead and work within G165 LFV. Continuing on, it can offer horizontal facing, vertical facing, taper, arcs, and drilling. So it offers a wider range of different programming and utilization skills. And it's also, again, it's easy to use in the programming format. As you can see below, it's G165 with your arguments, turning on the LFV. In between, after that, it's your normal machining program, and a G165 with an argument to go ahead and cancel the LFV mode. That easy. Moving on to mode 1 programming. With command formats and arguments, our Q value determines how much distance is moving in reference to the feed rate per oscillations. So basically, it's just the distance of your air cut. So in here, in this chart, is the unwrapped cutting path. The blue line is the amount of oscillations per revolution. So it's at a 1.5 oscillation. So every 1.5 during that 360 degrees, it's going to go ahead and oscillate in and out of that cut. Moving on, the D value is D value is specifies the number of oscillations per spindle revolution. So how many times is your tool or the part going to go ahead and go in and out of the cut? That's all you're simplifying there. Moving forward with a little sample program just to show you what it looks like with mode 1. Again, easy to use, easy to incorporate into any program. With the 165, do your machining in between, and after so you cancel your LFV mode and move on to the next operation. So here in this graph here, shows a setting parameter on LFV of a Q value of 2.0, which is your vibration rate, your D, which is 1.5, your vibration frequency, and a feed rate of 10 thou. And you can see here, this is going to be the first.
Let me confirm that's 10 microns, so it's a metric feed rate.
Sorry about that.
No problem.
So as you can see here, this is the blue line indicates your first rotation of cutting. The green line is going to be your second rotation of cutting, with the air pocket being right in here, which is going to go ahead, and that's going to go ahead and be basically your chip breaker. So in and out of that cut, and then it's going to go back in, hit, and continue.
And I'd like to add to this slide here, Brad. So if you look at the dotted line on the bottom from 0 to 360, that is what would be the normal path of a normal tool feeding. And so whatever the feed rate is, as the tool is traveling on that first green line, you can easily see that it has to go out at this triangle, if you will, and come back in and match the current feed rate. So the tool actually has to feed a lot faster than your feed rate in order to keep up with this process. And so that's why you'll see on the next couple slides, there's some limitations to a feed rate. But understanding this slide is kind of important, that this dotted line would be the commanded feed rate, and your tool has to travel further in two directions in order to get back every rotation multiple times. And so this is the whole idea of LFV, and just wanted to make that a little bit of a finer definition. So go ahead and please continue.
Thank you, Brian. So moving on, some more programming for mode 1. Just some notes that we have. Spindle speed can depend on the vibration frequency. Your max cutting feed up to 1 thou and a tenth. But note that with a feed of 30 microns, Q of 2.0 and a D value of 1.5. In this case, the amplitude, like Brian was saying previously, the cutting is going to be 3 thou and 1/10, but the actual cutting feed is going to be 9 thou and 4/10, so much faster. Commanding range of LFV mode 1. Your calculations of initial setting of your D values. Really quick, we've seen this video a little bit ago, but I just wanted to go ahead and touch on it one more time because it's so short, and it just shows how great this technology is that we have, and how it just works. And then quickly, I just also wanted to show you another test that I did in copper. On the left-hand side, this is LFV off. And on the right-hand side, this is with our LFV on, with our settings of Q 2.0, D of 1.5, and our feed at 1 thou and 2/10. And such a difference, but so continuing on, we move to mode 2. Mode 2, you have your same G165, but your arguments are going to be a little bit different. So getting into it, your E value specifies the number of spindle revolutions per oscillation. R value specifies the number of spindle revolutions required during retraction. Your I value specifies the compensation value for the vibration amplitude. And then quickly, I just wanted to go ahead and show you guys a quick sample program of how easy it is, again, to go ahead and just incorporate into your program. And how easy it is just to use. Continuing on, the number of spindle revolutions per oscillation is specified. As you can see in the figure below, you can see here the relationship between the feed and the revolution amount. Some additional notes for mode 2. Your max spindle speed depends on your spindle rotation per vibration. Your max cutting feed up to 2 thou. Commanding range of LFV mode 2, E of 1.5 to 6.0, and an R value of 0.5 to 1.0. Calculation of initial setting of E and R. And then just a quick video of LFV mode 2 doing its magic. So as you can see here, it's about every 2 revolutions causing a longer chip to be created and broken, and then moving back into the cut. And then out again.
Yeah, I'd like to add just a little bit here. So we can all say we want to break chips and we love these little chips, but you can actually make too small of a chip and it gets through your little straining system in your oil and it clogs your filters. And so often we want a good controlled chip, not necessarily a microscopic chip. So mode 2 gives us the ability we can program the change length of our chip. It's excellent. We can make it a 1/2 inch long, 3/4 inch long, 1/4 inch long. So very easy to program. And I would also suggest in topic that we always would try to make the least amount of settings possible. So Brad has some suggestions from Citizen on where to start with LFV. And it kind of comes real simple. Start low. The chips are not breaking yet. Increase your oscillation a little until the chips start breaking. And it's that simple. And we have total program control over mode 1 and mode 2 of being able to do any way you want to adjust it and change it. So very easy. And I just wanted to add that little point. So please continue.
Thank you, Brian. Just another sample pic of LFV on in mode 2. As you can see here on the left-hand side, all the chips are roughly about 1 inch long, very even. This material was 17.4, and our settings were an E of 5.0 with an R value of 1.0, and our feed rate at 2 thou. So very beautiful cuts. And I just want to get into mode 3 now. In mode 3, the x-axis is in sync with the spindle moving in and out until the last path, then at which point standard cutting is taking place with no LFV. And then I just want to go ahead and show a quick figure. On figure 1 here to the left, you can see a normal threading cycle. And on figure 2, you can go ahead and see the LFV threading cycle. The only difference is the X is oscillating up and down in the cutting of the thread. All the other movements are the same. Commanding format, again, same code, G165, instead with a P3 value, and then you have your arguments. First argument I want to go ahead and talk about is the D value, specifies the number of vibration oscillations per spindle revolution. Your E value specifies the number of spindle revolutions per vibration oscillation. And your Q value specifies the amplitude in-feed ratio that is used to determine the vibration amplitude. Your U argument specifies the guaranteed amplitude during LFV mode 3 as a radius value. The specified values remain in effect until LFV mode is switched or canceled. K value specifies the number of paths during your thread cutting. And an X value specifies your material diameter at the start of the thread cutting. Your I value specifies the compensation value for the amplitude for vibration during the thread cutting. And then I just wanted to show you a quick sample program using G32. You can see G165, and then after so, it's just your normal G32 threading cycle. Continuing to the bottom half of the threading cycle, continues same way, then just with the G165 to go ahead and cancel the LFV mode. And then you can move on to your next operation or process. And then just another program example of G92 being used. Same thing, G165, G92, and your threading and your normal threading passes. And then with the G165 to go ahead and cancel. Pretty simple.
So Brad, as this video plays, there's a couple questions, so maybe play it a couple times as I show the question. So there's a question, oop, I moved a little, give me a second. Does mode 3 use 2-axis or just one? Can you be turning on Z1 with LFV while OD threading on sub with LFV? So it's a multiple part question. The first question part is it's one axis. So we're threading in Z, but X is oscillating. And so the second part of the question is, can we work on the sub spindle just with Z? So I don't think I have the perfect answer, but I believe that since the threading is one axis and the subspindle Z would be one axis, that you actually could do both at the same time. I'm not 100% sure with that. Anybody else on today have the answer to that? So can we LFV thread while the subspindle is LFV peck drilling? So the threading portion of our LFV is newer to us, and we don't have tons of experience in the United States. So maybe we don't have that answer for you today, but I gave you my proposed answer. So then I have a couple more questions, not all perfectly pertaining to this, but let's get them out of the way. Okay. Where phase is required between spindle 1 and spindle 2, will LFV during cutoff allow 2 spindles to match phase? So I'm going to say yes, we've done that. So you can use spindle sync and then turn on LFV. Well, somebody make sure I'm correct. Can we spindle sync with LFV?
According to everything I've read, we can't.
We cannot. Yeah, so I guess we can't use spindle sync when we're cutting off with LFV. So that would be no. The answer would be no. What testing has been done Do you see any difference in cut time when you are just turning with LFV? Well, that's real simple in this presentation. We'll cover it in a moment, but as long as your feed is the same, there's no time difference with LFV. It has to do with if you have to change your feed rate or your RPM. So then this shows, can you summarize the max feed rate in inches for both mode 1 and mode 2? Pretty straightforward that in general, the maximum in mode 1 is 1 thou per rev. Depending on the settings that you do while using LFV, the tool has to move more than that. And we showed on the one slide for 1 thou per rev, it actually has to move 9 thou per rev to get there. So the maximum recommended feed rate for mode 1 is 1 thou per rev. Mode 2 is multiple revolutions per oscillation, so it can go faster, and that is a maximum recommended of 2 thou per rev. Now, that being said, may slow your process from a previous process, but you get full control that you can run unattended. The answer is how many parts are in the bucket at the end of the day, not just the cycle time. And we're going to cover a little bit more on the feed rate and the cycle time later in the presentation. So I will let you continue, Brad.
Okay. So as you can see, just really quick, you've been seeing this video play for the last 3 or 4 times now, but just as you can see, the x-axis is moving in and out of the threading cut, and it's keeping perfectly timed with the spindle rotation. Move on. Just some suggestions for programming. LFV does have a halt command, so you can temporarily turn off LFV in the middle of it. So if you were to go ahead and change spindle change directions in your toolpath, you can go ahead and you can call upon a V0, and that will go ahead and halt the LFV temporarily until you say otherwise. Some other things to know. We can use G44 and G43 with a D value to go ahead and make the rotary tool in inches per revolution instead of inches per minute. So that way we can go ahead and drill using LFV. Then LFV is available in your WinCNC. We do have it, so if you did have it open and you were to go to your surface footage and RPM info, it will be in your left-hand corner. It'll say big button of LFV, and in here it's going to have all the recommended D values and RPMs for your desired operation. So you can go ahead and do an auto calculation in there, and this would be a good place to start. This the same graph is also in all your manuals as well. The use of proper speeds and feeds. Again, this is just showing what a table of contents that can be used with your D argument. So it shows you a max RPM, and then it shows you how many your number of oscillations. Continuing. And then it also has arguments for your E, so you can go ahead and just get a quick reference as far as if you were to start at 1.5, you're going to be about at 1490 RPMs at that number of vibration oscillations. And adjusting for better performance. So some common questions. Does the machining time change when the cutting feed rates specified are the same as those for standard cutting? Machining time does not change if speeds and feeds are the same as standard cutting. However, there can be differences in the cutting that cause spindles that can cause spindle speed to be auto-adjusted by the LFV. Is there any way to achieve a better surface roughness? The surface roughness may be deteriorated due to tool pass and tool nose distances. If it happens, you can try a lower feed rate or rough with LFV and then finish with standard cutting. Is there
Hold
any
on
way?
1 second. I lost you for a second. Can you guys hear Brad at the moment?
Yeah,
Yes.
yeah,
We can hear.
yeah, I can hear him.
Is there any way to achieve better roundness? The uncut portions caused by tool nose radius does not stabilize due to tool pass, which may deteriorate the roundness compared to standard cutting. It is best to use lower settings if this becomes an issue, which I would always recommend starting at the lower settings anyways, and then moving up until you're happy with what you're seeing for results. You want to adjust the chip length. Chip length can be increased setting smaller D value in mode 1, and setting a longer E value can increase the chip length in mode 2. Our tool lives on inserts have become shorter. With LFV mode 1, a possibility that the set amplitude is excessive, so you can try decreasing the Q value and seeing if your tool life becomes greater. Concepts of inserts that work better. Some people ask where to begin with cutting and tools. I suggest tool type D tools 55 degrees with a nose radius of 8 thou. When the cutting allowance is large, try tools with a nose radius of 15 thou. As for breaker shapes, U breakers with sharp edges are very effective. Another good place to start is positive style inserts, ground geometries, tool nose radius 8 thou to 15 thou, low side cutting edge angle, as in the pictures here. So you want it to be 90 degrees or 93 degrees. In my testing, I found that having 90 degrees or as flush as possible was the best results. Crown chip breakers, just to show you the idea, we want the little to no hone ground insert with a ground chip breaker. So that's where I'd recommend for starting for your inserts.
So with that being said, we do have customers that use whatever insert they had and had good results and benefited, and they loved LFV. So that recommendation is just on a technical state. The common sense is the sharper insert's going to produce less cutting pressure. And so it's suggested, but it's not mandatory. So you'll have to experiment and see what of your inserts you use, or if you do change to some different kinds of technology. But for the most part, LFV just works.
So when using the LFV function, it has the following differences compared to conventional cutting. Your machining accuracy might be just a little bit different, such as your roundness, your surface, and roughness. There is potential restrictions of spindle speed and feed rate, which we already have talked about. Cutting tools, machining conditions, and cutting oils are different from normal cutting conditions. When specifying mode 1, if argument Q is set to 2.5 or larger, or if feed per revolution is set to 1/1000 or larger, the vibration motion of the feed axis may become excessive. So you'll start feeling the machine vibrate excessively. And then LFV also does not run in check mode. Just to show another good video of LFV just working. This is on the back side, and you can see those little chips just flew off, broke beautifully. Now with LFV off, you can see they're all stringy, got wrapped around the tool right there, maybe creating edge buildup. We've seen a little bit of this earlier, but I wanted to show a really cool video of it. And I think this demonstrates it, is grooving with mode 2. Just look how beautiful the chips are coming off there evenly. Moving in and out of the x-axis. So that concludes our presentation for today. I just want to thank you all for attending, and I will go ahead and open up for any further questions.
Sounds good, Brad. Thank you. And as we learned something on this Teams live event, my internet went out and I was gone for about 10 minutes, and you guys were able to continue, so that was great. But with that, there was a whole bunch of questions in the interim, and we have a lot of technical people in this event, and this was kind of meant to be a sales event. And so there's I don't want to say argument, but there's confusion in the questions. So there's so many, we're not going to get to them all, but I would like to address a couple of them. And so first of all, I do believe we can use spindle synchronization and LFV, but only in the x-axis. And for absolute confirmation for that, there's a small chance I'm wrong, but the manual says it specifically, and we can get you that information for the final answer. Then there was a few statements and questions on the threading mode, and one of our engineers had done some testing, and I only know from looking in the manuals that there's many suggestions, but if I try to summarize, if you could imagine whatever your normal threading was, you have to do 2 times the passes. And our engineer's suggesting he needed about 3 to 5 finish passes. The manuals explain like 2 finish passes, but if in simplest case, LFV threading is probably double the cycle time. But that being said, if it's an Inconel or a tough material, and we're going to break the chips and have a good process, the cycle time doesn't matter. It's how many parts in the bucket at the end of the day. And so as we're still learning LFV thread mode, basically, it does just work. There's some question on the pullout, and I know the manual has many suggestions for the angle of pullout, and you basically program it. This presentation isn't to explain that. Another said, is LFV mode added to Esprit? And I believe I can say it already is. Exactly how you utilize it, I don't remember. If you use Esprit's post manual, it will explain it. I know it's in there. Then another gentleman said LFV is also coming available on Elkhart Wizard soon. So that's good. So that's our second software that we use in the United States for program editing is the Wizard. And they also will be helping to support LFV spindle RPMs. There's more questions here. Let's see. Well, actually, I think that's most of them. Now I got some new questions. Here we go. So will LFV be available on the subspindle of the L20? It's been determined that the design and structure of the L20 on the subspindle side having to do with the Y2 axis, it's just not possible to make it strong enough to withstand the vibration. So at this time, the L20 subspindle type 10 and 12 will not function LFV. Another one, anonymous. So why is the feed rate limited to 2 thou per rev in mode 2? It seems as if it was rapid speed limitation. A slower spindle speed would allow for a higher feed. Well, you have to remember that the tool has to back up and come forward. So a 2 thousandths per rev feed, the tool's actually moving probably 10 thousandths, 12 thousandths on the vibration. This is why there's a maximum feed rate, and it happens to be 2 thou. For what it's worth, you can go more. It's a suggestion. When you run your machine and you do use the higher values, you will feel the vibration. And so, we don't want to, in the long run, hurt the machine. And so we have a suggestion of a 2 thousandths maximum. Boy, there's so many questions. Another person commented, our slide presentation stated that LFV does not work in check mode, and this statement is correct. Just like threading on our setup process, if we press actual cut, then LFV actually will function in our machine program check mode.
Okay.
Here, this is a good statement. It was a good idea, and I'll let you comment, Brad. Please elaborate a bit more on the comma V0 statement. I think it's a powerful argument. So you don't have to jump out of LFV and back in. So if you want to comment, Brad?
Yeah, it's a very powerful argument in G165 or within your program that you can go ahead and do a comma V0, and you can simply turn off temporarily the LFV and change directions and increase your feed, and then go back into your normal cut, and it will go back to your standard LFV feeds.
Yeah, so what we found is many people might turn at 1 thou per rev, but when they come to the x-axis, they might go 4 thou per rev and then go back to 1 thou per rev, and it would be very easy to not think, and your machine will do it. I'll even say when I check some of our people at shows and open houses, they kind of forget this. And so I suggest, hey, let's add the comma V here. You know, it's very easy to do. And so that is a very good feature. And thank you for asking the question. There might be one or two more if we hold off for a moment. There were so many that, and some of them are repeating, so I'm sorry. A question, does G165 without arguments, does it set the arguments automatically based and RPM? So I believe Brad covered it. If you don't put something in, there is a default value, and then whatever your RPM was, it would just change. But I wouldn't recommend that. You want to know exactly what you're doing, and you want to know the RPM before you cut so that your surface footage and things is correct for your cut, and then use LFV. And this is why we give you the tool. So one is in the manual. Unfortunately, nobody likes to pick up the manual. So we added it right to WinCNC. So you can go into WinCNC and click the button, and you can at least know what you want to do, see what's available for the LFV RPMs, and make your process prior to going to the machine, and you'll just be a lot faster off. Okay, so basically that's about it. I would like to take this opportunity to thank you all for attending. Also, Brad, thank you for your presentation. For those still with us, we have a couple more events next week, some sales and some support. I know one of them is our B-Axis review. So if you work with your distributors and the people who sent you these invites, you'll probably get some more, and we welcome you to join. We'll sign off this meeting. I'll end in saying, please stay safe. Thank you for your attendance from Marubeni Citizen, and have a great day. Thank you.